Thank you very much. I'm Sean. I'm one of the co-founders and chief hardware architect at Cerebras Systems. When we started Cerebras, we had a vision and a mission to really drastically change the landscape of compute for AI. We wanted radical improvements, and we knew that to get radical improvements, we needed radically new hardware. So to solve the problem of deep learning compute, at Cerebras Systems, we have built the world's largest chip. And that's what that looks like. That's our chip. It's a single piece of silicon. It's over 46,000 square millimeters. In that size, we can pack 1.2 trillion transistors. That's powering over 400,000 AI-optimized cores. And these cores are fed by 18 gigabytes of super fast on-chip memory with an unprecedented 9 petabytes per second of memory bandwidth. And it's all connected with a fully on-chip fabric with 100 petabits per second of bandwidth. Now, that's a lot of big numbers. But how big is this chip really? Well, it's pretty big. It's in fact the largest square we can carve out of a 300 millimeter round wafer. It's actually 8.5 inches per side. It's like the size of a piece of paper. The Cerebras Wafer-Scale engine is 56 times larger than the largest GPU today. And we built a system around it. The Cerebras CS1 system is a full solution in a box. It's powered by the Wafer-Scale engine. It's programmed using TensorFlow, and it installs in a standard data center rack. This is what makes it the world's most powerful AI computer. Now, that's pretty cool, but the question is, why does this make sense? Well, the answer is that deep learning training is hard. It is fundamentally hard because of both the size and the shape of the problem. The size of the problem is extremely immense. We need billions to trillions of operations to train for each sample, and then we need millions to billions of samples to train a single neural network. You multiply those out, and we are in the peta to exascale compute range. The shape of the problem is also extremely challenging to scale. It's very interesting. At the fine grain, there's a lot of parallelism. And that's great. That provides a lot of opportunity to accelerate. But at the coarse grain, the problem is inherently serial. Right? Training is the act of incrementally small changes applied to a neural network over time, one after the other, serially. And so both the size and the shape of the problem make training neural networks very challenging on today's architectures. So the natural question is, well, what is the right architecture for training neural networks? An architecture optimized for deep learning compute has these key properties. It has a core optimized for neural network primitives. The core is flexible and programmable because neural network architectures are evolving every day. It's designed for sparse compute because neural networks are naturally sparse. Memory is all local because weights and activations in neural networks are all local to each layer. And lastly, we need a fast interconnect because layer-to-layer communication in neural networks requires high bandwidth and low latency. So next, I'm going to describe these in a little bit more detail. The foundation of any architecture is the core. A core optimized for deep learning has two key properties. The first is that it should be very flexible and programmable. And that's because ML researchers are coming up with new neural network techniques every single day. Second, the core should be optimized for tensor operations. And that's because neural network compute is primarily tensor operations. So our core is a fully programmable processor with a full array of general purpose instructions, such as arithmetic, logical, load, store, branch, all the stuff that we are used to in general purpose processors. On top of that flexible foundation, we have high performance tensor operations for ultra high performance data processing. In this core, tensors are in fact first class operands right in the instruction set architecture itself. This is an example of a fuse multiply accumulate instruction where it's operating directly on 3D and 2D tensors in the same way that an instruction might operate on a register or a memory location. When designing a core, you have to consider sparsity. And the reason is because neural networks are naturally sparse. Common ML techniques, such as dropout, such as ReLU, introduce a lot of natural sparsity in neural networks. If you designed a core optimized for the dense network on the left, when really the compute looked like the sparse network on the right, that's quite wasteful. So our core has native sparse processing in the hardware itself. This is done using data flow techniques, where all compute is triggered by the data. This allows us to filter out all of the sparse zero data and skip all the unnecessary processing. This is all enabled because of these fine-grained data paths, basically these 400,000 small cores all acting together can provide very efficient processing for dynamic, non-uniform work. The next main component of any architecture is memory. A memory optimized for deep learning should be local and should support high performance when there's low data reuse. And the reason for that is because memory used in neural networks are used for weights and activations. And these are all local to each layer within the neural network. So traditional memory architectures are not well optimized for deep learning. And the reason is because they're central, slow, and they're far away. They're typically off-chip DRAM. To get performance in a traditional memory architecture, you need caching. And for certain applications, that works reasonably well. However, the fundamental operation in a neural network is a matrix vector multiply. The matrix is the weights, the vector are the activations. And a matrix vector multiply has no data reuse. And so caching techniques are not effective. If you ran this directly on a traditional memory architecture, your performance would be very low. So the ML community has worked around this by running multiple parallel vectors, making that matrix vector multiply into a matrix multiply, which has a lot of data reuse. And this technique, as we all know, is batch or mini batch. Now, that works to drive up the memory utilization and performance, but can have undesirable training characteristics. So our memory, which is optimized for deep learning, is entirely distributed with high performance, local SRAM only. That means all the memory is fully distributed along with the compute data paths. This allows full performance from the memory into every execution unit, allowing us to run that fundamental operation matrix vector multiply at full performance regardless of batch size. So the last component of any architecture is the interconnect. And here, an interconnect optimized for deep learning compute must support local communication at high bandwidth and low latency. And the reason for that is neural network communication is largely local from layer to layer. Even complex neural network topologies that have connections like residual connections or skip connections, the communication is still generally pretty local. So our Fabric interconnect is fast, it's fully programmable. It uses very small single word messages, and it's all baked into the hardware with zero hardware overhead. The topology is a 2D mesh, which is extremely efficient for local communications like that of neural networks. This allows us to get high bandwidth and low latency and very high utilization and efficiency compared to global topologies. But to achieve the radical performance gains that we were looking for while training neural networks requires more compute than we could fit on a single traditional chip. We need more cores, we need more memory, we need more fabric bandwidth than we can fit on a single traditional chip. This is what we need. We need to build really big chips. By building a wafer-scale chip, we can combine the massive compute, high bandwidth memory, and ultra-fast interconnect at a scale never seen before. It lets us run cluster scale performance on a single chip. That's because we have 400,000 cores. It allows us to put gigabytes of memory one cycle away from every execution unit. That's impossible with traditional memory technologies. And it allows us to use a fully on-chip interconnect that scales across the entire wafer uniformly with uniform performance. That's orders of magnitude higher performance than traditional off-chip interconnects. So now I've described the key components of our architecture. We have 400,000 cores. So the question is, well, how do you use all of those cores to train a single neural network? The wafer-scale architecture enables a spectrum of parallel execution strategies. Options along this spectrum have different training characteristics. And so by supporting all of these options at high performance, we provide full flexibility to the user to use the option that fits their needs. One axis of the spectrum is data parallelism. And this is when you run multiple samples of the input training data set at one time on your devices. The other axis of the spectrum is model parallelism. And this is when you run different parts of the network at the same time on your devices. Now, to demonstrate how the wafer-scale architecture enables all of this spectrum at high performance, I'm going to describe a few of the options and illustrate how they leverage architectural properties. So first, to set the context and for background, let's look at how we train on a single GPU today. The execution strategy on a single GPU today is layer sequential, where you run one layer of the network at once. This is illustrated in the picture on the right. Suppose you have a 3-layer neural network. Execution proceeds from top to bottom in time. At first, you run layer 1, the blue layer, across the entire GPU. Then you run layer 2, and then layer 3, you hit the end of the network. And then you run the layers back in reverse order for the backwards pass for deltas and gradients. And then finally, you update the weights. On a GPU, this style of execution requires a medium-sized batch because of the GPU memory architecture constraints I mentioned earlier, but gives good performance while it's constrained to a single GPU. So next, let's look at how we traditionally scale out to a cluster of GPUs. And here, we use high levels of data parallelism. In fact, we just had a talk about exactly this technique. Right? We run multiple replicas of the neural network across all the devices, one replica per GPU. And each of the replicas essentially runs as it would on a single GPU. And then at the end, we do a weight synchronization step before we do the weight update to make sure that all the replicas have the same weight. This is a traditional way of scaling to a cluster of GPUs, primarily because the communication is very low. In fact, the GPUs are not communicating with each other at all until the weight synchronization step. And so this makes it very well suited for traditional interconnects like Ethernet, like InfiniBand, like NVLink, which are relatively low in performance. So this works, but the downside is you get extremely large batch size. You need a medium-sized batch in each device just to get the performance up because of the memory architecture. And then you have a large number of devices. And so while you can keep all of these devices busy, such a large batch size can result in convergence challenges. In fact, training at large batch is so hard that successfully doing so at performance is very often publishable research. In fact, we just had talks about it, right? It's hard. And additionally, even though it's relatively low communication between the GPUs, we still have a weight synchronization step that needs to happen. And although there are all sorts of tricks that you can play to overlap much of that communication with the compute, you can't overlap it completely. And so you still have a non-trivial overhead from communication. So when you pull all of this together, the traditional extreme data parallel way of scaling to a cluster of GPUs today gives nonlinear performance scaling. You get scaling, but it's costly and it's inefficient. So the question is, how can we do better? So let's start by just looking at how running the same execution model on the Wafer-Scale architecture would look. Here we have multiple replicas of the network, and we run them the same way as we do on the cluster of GPUs. But instead of running one replica per device, we run one replica in a section of our fabric. And we only have one device. Execution proceeds exactly the same way, weight synchronize, and weight update at the end. But the exact same execution model on the Wafer-Scale architecture has several benefits. First, the batch size is much smaller because each replica can run with a much smaller batch due to the memory architecture. Second, because of the ultra-high bandwidth and low latency interconnect, it's on chip after all, the weight synchronization overhead is also much lower. And so the result is you get much closer to linear scaling with a medium-sized batch, similar to a single GPU. So that's pretty cool. But if we stop there, we're not taking advantage of all of the benefits of the Wafer-Scale architecture. The first thing to note is that the number of replicas and the size of each replica of the neural network is not constrained to the device boundaries, right? We only have one device. It's in fact more a function of the layer size. And so for very large layers, you can actually stretch it and run it across the entire wafer. And this is enabled by the ultra-high bandwidth interconnect, since it's all on chip. Right? This is like running a single layer of a neural network across an entire cluster of GPUs. When you do that, since there's only one instance of the network, there's one replica, the execution proceeds very similar to how it does on a single GPU. Right? You still go through the layer sequential execution. At the end, you do your weight update. But the benefit is since there's only one replica, you get a much smaller batch size, right? Because of the memory architecture benefits I mentioned. And since there's only one replica, there's no weight synchronization overhead. So the result is you get much closer to linear performance scaling with a much smaller batch on really large networks. This is actually very impressive. But the natural question is, well, can we get these properties for networks of all sizes? And so to answer that, we turn to layer sequential execution. And this is a model parallel technique. Sorry, I meant layer pipelined execution. And this is a model parallel technique, right, where we run all the layers of the neural network simultaneously at the same time, each layer running on a different section of the fabric. We run these layers in pipeline fashion. And this is all enabled by the ultra-high bandwidth on-chip interconnect that we have. This is shown in the picture on the right. You start by running your first layer, the blue layer, on a portion of the fabric. Then you move on to layer 2, the green layer. But while you're doing that, you run the next sample into layer 1. And this continues in pipeline fashion until you hit the end of the network and you run the back pass. And in steady state, every layer of the network is running at the same time simultaneously, both forward pass and back pass of the training. When you do all of this, you have a medium-sized batch. And the reason for that is because the batch size is actually proportional to the network depth. And that's because we want to amortize the fill and drain overhead of the pipeline. In fact, you can see the fill overhead here, the white triangle on the top. And when we hit the end of the batch, we have to drain the pipeline, and there's a drain overhead as well before you do your weight update. But the weight updates themselves have no synchronization required because there's only one instance, one replica of the network on the device. Weights are all just updated in place. And so here now we have linear performance scaling with a medium batch size that's similar to a single GPU. Now we can do even better than this. Because using a technique called pipeline backpropagation, we can update the weights without draining the pipeline. This allows us to essentially run the pipeline fully in steady state, every layer running simultaneously, occupying the entire resources of the wafer. And we can take our weight updates at an arbitrary point in time. This is enabled by the memory architecture. There's still no weight synchronization overhead because there's only one instance of the network. Now, there is a trade-off, because when you do this, you can introduce a small difference between the weight seen on the forward pass and the back pass. For medium depth and shallow networks, this difference is not a problem at all. For very deep networks, we have shown that simple momentum-based techniques can be used to compensate for that forward and backwards delay, and you can still achieve full convergence and full accuracy. So when you do all of this and you pull it all together, what this gives you is linear performance scaling with an arbitrarily small batch size. You can go down to batch size of 1 if desired. That's cluster scale performance with an arbitrarily small batch size. This is the potential of the Wafer-Scale architecture. We believe this is what enables ML to be done the way that ML wants to be done, and not constrained by hardware limitations. So I've described the spectrum of parallel execution strategies. All the options along that spectrum have different training characteristics. By supporting that spectrum, all at high performance, we give full flexibility to the user to choose what meets their needs. All of this is enabled because the Wafer-Scale architecture was designed from ground up to run deep learning at scale. This gives us cluster scale performance on a single chip. making the CS1 system the world's most powerful AI computer. And this isn't just an idea, but the CS1 system with the Wafer-Scale engine, it's up and running real customer workloads at scale today. Contact us if you're interested to see how your models run on this revolutionary new architecture. Thank you very much.
Questions for Sean? We have a question there.
Hey, Sean, I actually read your white paper, and it's pretty impressive how you guys are able to design the redundancy into the cores just like how DRAM is. Can you explain a little bit how that works and what's the underlying programming to make sure that the cores work with the redundancy?
That's a really good question. Clearly, building a chip of this size, one of the biggest challenges is yield. Right? You cannot actually yield a chip of this size with 0 manufacturing defects, even on a very mature process. And so to make this work, right from the beginning of the architecture needs to consider redundancy. And so here what we do is we have both redundant fabric connections and redundant cores built into the hardware, similar to DRAM. And the way we repair defects is we detect any defect within a core. Could be a logic defect, could be a memory defect. And we map out that core. And then we use our redundant cores to take its place. But the key then is that we actually use our redundant fabric links to reconnect the fabric so that it still logically looks like a full 2D mesh. So everything except for the most lowest level software sees a fully formed fabric. And when you do that, actually, it turns out you can actually drive your yields very, very high, much higher than even a lot of big chips today.
Let's thank Sean one more time.